Log on, tune in, find out. Another good idea from Cambridge.
Give a talk closely related, I think, to the last two on designs for mixed models with binary responses.
So this talk follows on fairly directly from what Dave Woods was just saying, and in particular we're going to zoom in on the kind of other approach that Dave mentioned. So that's design really for conditional models. So to begin with, I'm going to recap some of the kind of motivating problems and background to what Dave said. I'll then go on to define the models that we're working with, in other words, the generalized linear mixed models. And really the hard thing about design for GLMMs is that the information matrix is difficult to evaluate. So to get around that, we're going to look at some cheap analytical approximations to the information matrix. So I want to discuss a bit about where those come from and what they look like. We assess the relative ability of the different approximations to produce designs using a couple of different things. So we've got a benchmark problem and also a more detailed computational approximation that will allow us to essentially evaluate maximum likelihood designs in the case where there are a few points per block. We'll round off with some examples of Bayesian designs computed using the various different methods. So to refresh our memories then, there's a sort of increasing recognition of this need to design experiments where the response is not normally distributed or more generally can't be modeled using a linear model. And one of the more extreme examples of this is really the case where you've got a binary response, so something that can be coded just using two levels. And there's all kinds of examples where you might have a binary response. So for instance, I might be doing a bioassay in which I'm interested in whether some insect either survives or dies following the administration of some interesting virus. I could be doing a crystallography experiment in which I'm interested in how various different factors affect the probability that a crystal is either formed or not formed. Or I could be doing some kind of engineering experiment in which I'm interested in whether a coating on a bearing is either cracked or intact. It's often also the case that our experimental units kind of divide up into these homogeneous sets in which the responses are more similar. So one reason why this might be the case, you could be doing an experiment on some kind of components in manufacturing where units which come from the same manufacturing run are more similar. We might be doing some kind of animal experiment in which there's things in common between individuals in the same family or litter. Or we could be taking multiple observations for a particular individual, and obviously those tend to be correlated. So a class of models which can neatly capture both of these features is the generalized linear mixed models. And really the sort of defining feature of these models is this stochastic vector of random effects, which we're going to call UI. And the idea is that conditional on these random effects, the distribution of the responses in a given block is going to be an exponential family, and the different responses are going to be independent. So this exponential family is going to have a mean mu, which is related to some treatments, which we collect together in a vector x. And we've also got some regression parameters, beta, and there's some dependence on these random effects. So this thing on the left-hand side is the link function, as I'm sure has been said before. And this expression on the right-hand side is referred to as the linear predictor. So we also need to make some assumptions about the distribution of these random effects vectors. And we're going to assume that they're multivariate normal with mean 0, and that the different random effects vectors from different blocks are independent. So a specific example of this model then is the logistic random intercept model. And in that case, we've got a Bernoulli or binomial response distribution and logit link function. So this is just the log of the odds of success here. Another simplification that happens in this model is that this vector of random effects actually collapses down to a scalar, and in which case the predictor simplifies to this form that I've shown in red here, although I don't think we can actually tell that it's red. The kind of designs we're going to work with are what we call approximate block designs, in which the block is of a fixed size. So what this means is that our design is essentially a collection of blocks where a block is just a set of m treatment vectors, together with associated weights for each of those blocks, such that the weights have to sum up to 1. And the interpretation is that essentially these weights describe what proportion of the available experimental blocks should use these treatments that are contained in, say, zeta I. So as an example of that, you might have an experiment in which there are 2 factors, and you have 2 blocks in your design of equal weight, and the treatments in this particular design are given in these figures. So yeah, this horizontal axis is the first factor and the vertical axis is the second factor. And the idea is that we should use these treatments for half of our blocks in the experiment, and for the other half of the blocks in the experiment we should use these treatments. So we're going to be seeking designs which optimize the value of some functional of the Fisher information matrix. So an important problem is the evaluation of that information matrix. And note that we're going to focus on the information matrix for the beta parameters. So because these different blocks in the experiment are independent, we can rewrite the information matrix for the entire design as a weighted sum of information matrices for each block. And the information matrix for a particular block is just given by this usual negative expected Hessian of the log likelihood. So we can approximate this fairly directly by what we call complete enumeration, which basically involves considering each possible outcome in every block. But doing so involves a sort of huge amount of numerical integration, and it's very computationally intensive. So later on I'll talk about a kind of shortcut method which allows you to do that in some simple cases of the model, but in general it's kind of a hard problem. So just to give a bit more background on why this is difficult, well, this first expression just uses the definition of expectation to write out the information matrix as a sum over all possible outcomes. And that expression is in terms of this likelihood P, which is sort of an awkward thing because it's really a marginal likelihood. You have to integrate out over all the potential values of the random effects. Now, because this integral doesn't have a closed form solution, it's analytically intractable, you're going to have to do some kind of numerical integration, typically some sort of quadrature method. So you're going to have to do 2 to the m integrals of this form just to be able to evaluate these p terms on the right hand side, and that's before you've even started to worry about these derivative terms over here. Because that likelihood is intractable, the derivatives are going to be reasonably awkward as well, so you're probably going to end up doing some sort of numerical differentiation. So you're going to have to evaluate p at some huge number of thetas and do some finite differencing, etc. It's all going to take a long time. If you use this kind of method, you're going to be waiting for a good few months before you end up with an optimal design. So having established the need to develop some cheap approximations to the information matrix, I want to talk a bit about, well, a suggestion. And this is really sort of dates back to something in the estimation or inference literature, kind of in the sort of early to mid-90s. And these revolve around some quantities that are called working variates. And basically all a working variate is something which can be computed given A, the data, and B, some current estimate of the linear predictor. And the form you have for the working variate is this sort of expression. The particular form of the estimate of the linear predictor that you use depends on the precise flavor of the method. So for instance, you might have what's referred to as marginal quasi-likelihood or penalized quasi-likelihood. And under the first of those, you basically assume that the random effects are sort of sufficiently small that you can neglect them in your estimate of the predictor. And you just plug in some kind of estimate of the betas. For penalized quasi-likelihood, you worry a bit more about these random effects. So you actually use a prediction of those random effects as well as an estimate of the betas. And the idea is that that's kind of supposed to work better if your random effects variance is reasonably large. really the key thing about these working variates is that they can be shown to at least approximately follow some sort of linear model. In other words, T is approximately F transpose beta plus some kind of stochastic component. I don't think Doug Bates will like this particular expansion here, but we've got some stochastic component on the right-hand side, which has expectation 0 and some variance which can be, well, which is either known or can be approximated reasonably well. So the idea behind the kind of estimation algorithm is that given some particular estimate of the linear predictors, we can plug that into the working variates and then use this model. So we regress those working variates on the model matrix, and that gives us an estimate, or an updated estimate of the betas. But once we've got that updated estimate, we could go back to the working variates and recalculate those. And so we can kind of iterate around there until we get some sort of convergence in the betas. The thing is, because we're using linear model theory, there's a kind of natural information matrix at each step of that algorithm. And if we think about what that approximation is, then for a sort of general approximate block design, we'll get this kind of expression. And you see that all you need to plug in is essentially the model matrix and the kind of variance-covariance matrix of the working variates. So if we actually do that for MQL and PQL, then these are the fairly horrible expressions we get. But the thing is that these are sort of analytical. You know, there's no integration left to be done now, so if we use these, everything will be much faster. This does have some precedent in the design literature, so for instance, for MQL, see the papers of, see these two papers. PQL has also got some history, so for instance, this paper by Tekel et al., but actually the PQL that they use is kind of different to what we're doing. There's some different approximations involved. I should mention that both of these are what are referred to as first-order methods, and there's also second-order methods, but you know, I'm not going to write up what those are. So much as for generalized linear models or non-linear models, the optimal design depends on the unknown values of the model parameters. So to kind of get around this, we start off by encoding our beliefs about the parameters using some kind of probability distribution. And then we find the design that optimizes the value of this objective function of Firth and Hind. So this objective function, or rather this family of criteria, generalizes the sort of usual mean log determinant criterion that people use to find Bayesian designs. And for alpha at most 1 over p, you can show that this objective function is concave, and so the thing satisfies the general equivalence theorem. So we're going to actually work with alpha equal to 1 over p rather than 0. And the reason that we do that is basically to make sure that our objective function is finite, even in the case where our prior distributions have unbounded support. And we wouldn't be able to do that essentially if we were using the mean log determinant. So that will allow us to use priors such as, for instance, normal priors or log normal priors, which we wouldn't be able to do otherwise. To sort of see why we wouldn't be able to do that otherwise, we need to think back to our model. And basically the observation you need to make is that as the value of these parameters gets big, then you get a kind of uninformative experiment with high probability. So if the betas are big, then you basically get the problem of complete separation. Whereas if the sigma squared parameter is big in this random intercept model, well, basically this linear predictor is going to be completely swamped by the random effects. So here I've got a nice little picture of the relationship between the linear predictor and the probability of getting a 1 for your response. And the idea is that if we're in a block in which the random intercept is large and positive, this is going to be all the way over here. And so essentially we'll get 1s for all the responses in that block. If, on the other hand, we're in a block in which the random intercept is large and negative, we'll be all the way down here, and so we'll almost certainly get all zeros. And in probability, each of those outcomes happens with probability 1/2, essentially, for large values of the parameters. So the thing is that if you get that kind of data, you're not going to be able to estimate sigma squared because you get the same picture for any big sigma squared. So you've got a risk that as these parameters tend out to infinity, your information matrix goes to 0, your log determinant tends to minus infinity. In other words, unless your prior density decays quite quickly as the parameters go out to infinity, that integral, the mean log determinant, isn't going to be defined. It's going to sort of not converge. So we want to avoid that problem, essentially. The problem is, in practice, if it doesn't converge, you're not going to be able to tell that it doesn't converge by doing some sort of quadrature scheme. Okay, so the only problem really left to mention in terms of the evaluation then is doing the integration. So evaluating those expectations with respect to the parameters. And we do that by using numerical quadrature. So we're going to use the method of Gottwald et al. Alternatively, you could do some kind of Monte Carlo sampling or Latin hypercubes, but we stick with quadrature. Once we've obtained our Bayesian designs, we're going to assess them in terms of the local efficiency distribution. So as Dave was saying in his talk, essentially for any value of the parameters, you could go off and compute the locally optimal design. And if you compare your Bayesian design to that locally optimal design, that gives you a sort of local efficiency. But the fact that we've got a distribution on those parameters induces a distribution on the efficiencies, and it's that efficiency distribution that we use to assess the robustness of the design. Okay, so for our first example, we're going to look at logistic random intercept model with 2 factors and 4 points per block. We have this kind of prior on the model parameters. So we've got normal priors on the beta parameters and a log normal prior on the sigma squared parameter. We've got these kind of middling values of the actual means of that, and we use a common variance of 0.5 on all the normal distributions. So if we go away and compute our optimal designs under each of 3 different methods, that is MQL and PQL that I was talking about before, and this MQL2 is just one of the second order methods, then we find out that each of our optimal designs consists of just 1 block, and these are the treatments in that design. So really the thing to notice, I think, here is that all the kind of design points are pretty close together under each of the different approximations. And that kind of correspondence can be formalized by considering efficiencies. So to do that, we need a notion of the sort of Bayesian efficiency, and this is the one we've gone for. But really the important thing is this table. So what this does is shows the efficiency of each of the designs under each of the different approximations. In other words, this entry here is the efficiency of the PQL design under the MQL approximation. So when we evaluate this thing here, we're actually using MQL information matrices. The important thing is that all these numbers are really close to 1, so there really is some sort of strong correspondence between the different methods. For our next example, basically everything's the same, except we've increased the variance on these beta parameters up to 3. So essentially we're just saying that we're more uncertain about the values of the parameters. If we do that, then as you might sort of anticipate, you need more blocks in your experimental design. In other words, you've got a wider range of situations to cover. But once again, we've got this kind of correspondence between the answers from the different approximations. Again, that can be formalized by looking at efficiencies, and in fact we do even better this time. We've got some numbers that are really close to 1. So. Okay, let's now assess these designs in terms of their efficiency distributions. So what we've done here is essentially, for each of the prior distributions, we've generated a sample of 1,000 vectors from those distributions. We've then gone off and computed the optimal design for each of those sampled parameter vectors using the MQL approximation, and then we compare the Bayesian design to each of those locally optimal designs, again using the MQL approximation. And what this figure shows is some kernel density estimates of those empirical distributions. So the thing you can really see is that under the second prior, i.e. the more diffuse prior, you get a much broader range of efficiencies. And you could kind of expect that because you've got to cover a broader range of situations in that, under that prior. It's sort of interesting to ask how well you might have done if you used a more naive method, particularly given that that first optimal design that we saw, the treatments didn't look totally far away from the sort of factorial design, the 2 to the 2 factorial design. In other words, treatments at each corner of that square. So here we've gone off and done the same calculation for the efficiency distribution for the factorial design, and that's this dotted curve here. And this other one is for the Bayesian design under the first prior. So the thing that you can see, again, while the factorial just kind of has this more diffuse efficiency distribution, in other words, there's a broader range of efficiencies, and on average that efficiency is lower. So you can see that again from some sort of simple summary statistics. So the first quartile and median efficiencies of the factorial are about 10 percentage points behind the Bayesian design. This last column shows that the Bayesian design can be expected to do very well under a much greater proportion of scenarios, essentially. So specifically, the Bayesian design runs at more than 90% efficiency under 2/3 of scenarios, as opposed to the factorial, which does that at 37%. However, you could have kind of expected worse performance from the factorial. It wasn't horrendous. And it turns out the reason for this is that essentially the values of the betas in these examples are quite small. So here what we've got is a plot of this sort of overall size of those beta parameters versus the efficiency of the Bayesian design at that particular parameter value. So you can see for the factorial, for small values of the parameters, the factorial design is essentially optimal. But as you increase the value of the parameters, that performance drops off quite quickly and becomes a lot more spread out. With the Bayesian design, you don't really get that pattern at all. It's reasonably robust to the different values of beta. So to summarize what we've seen in those examples then, first of all, more prior uncertainty gives you more blocks in your optimal design, as you might anticipate. Secondly, for these kind of moderate values of sigma squared, the answers from the different approximations look very similar. We gain some information compared to doing something really naive, like using a factorial design or a GLM design, because we wouldn't know how to allocate those points to blocks. So, the designs did improve on the factorial. We'll actually see later on an example in which the improvement is more dramatic. So for larger values of sigma squared, these approximations stop agreeing. And it'd be nice to be able to tell whether sort of one particular approximation does better. So what we'd really like is an independent arbiter of the ability of these different approximations to produce designs. And to some extent, that's provided by a benchmark problem. So here we're going to look at the logistic random intercept model again. And basically what we're going to do is fix some treatments, consider allocating those treatments to blocks in a few different ways, and vary the model parameters and essentially see what happens. So we get those treatments from a GLM design, a 4-point GLM design for the model in which we essentially kill these random effects. And if we do that, these are the treatments we obtain. And we're going to consider allocating these treatments to blocks in two different ways. So the first way is to put everything on the left-hand side in the same block, as indicated by colour. Right, well, if we do that, then the level of x1 is constant within that block, and it's constant within that block. So this design confounds x1 with the effect of blocks. So you might anticipate that this is a pretty poor choice. The second allocation we consider is to put opposing corner points of this parallelogram and group those together. So if we do that and calculate efficiencies for varying values of sigma squared, then this is what we obtain under the different approximations. So this thick black solid curve is the efficiency of the first allocation compared to the second allocation so in other words, using that second allocation as a reference. And basically we see that the correct pattern is as the blocks increase in their effect size, so as sigma squared grows, the efficiency of that first allocation decreases. If we work out the same thing under MQL, then we get the same pattern, although we find that MQL tends to exaggerate the importance of selecting the second allocation. Under PQL, something a bit strange happens. So initially we get this decrease in the efficiency of the first allocation. Then it kind of hits a minimum around here and starts increasing back up to 1. So essentially, for moderately large values of sigma squared, PQL is insensitive to the choice of allocation. And you can show analytically that that's always going to be the case as sigma squared tends to infinity, but here we've actually observed it for some kind of realistic values of sigma squared. So another thing we can do is look at our more detailed computational approximation. And that will allow us to essentially evaluate maximum likelihood designs in the case where there are fewer than 2 points per block. So the first step on the road to doing that is to realize that this information matrix can be written as F transpose WF, where F is a model matrix and W is this weight matrix, which involves a sort of complete enumeration type term. The thing is that given sigma squared, this weight matrix only depends on the vector which contains the fixed parts of the linear predictor. And that's nice because if we can sort of go away and pre-compute this W matrix for essentially all values of eta that might be relevant to our design problem, then we can find GLMN designs almost as easily as we can find GLN designs. So what we actually do is pre-compute this W on the kind of grid of eta values. And then to get W at points in between that grid, we're going to use some kind of interpolation scheme. So we actually use bilinear interpolation. And in some sense, if you do that, you get Bayesian designs for free because this W only depends on eta and not directly on x and beta. Once you've computed your lookup table, you don't have to do any extra evaluations of W in order to get Bayesian designs. This is going to be practical only for a small block size. It's not a panacea in any sense. There's a couple of reasons for that. First of all, cursive dimensionality. As your number of points per block increases, this grid that you have to evaluate on gets huge. Secondly, even if you can do that, suppose you can populate your grid, then your lookup time for a huge grid is also going to be huge, and it's probably going to take longer than just evaluating the integrals on a kind of case-by-case basis. So we're working with block size 2 in this example. Very similar model to what we've had before. Sigma squared's a bit bigger now, however, and also we have some rather substantial uncertainty a priori about the value of beta 2. So we assume that beta 2 is uniform on 0, 10. If we go away and compute optimal designs, then we find that the optimal design has a rather large number of blocks. So this is the optimal design under maximum likelihood at, in other words, that computational approximation, and MQL. We can see again that there's a rather strong correspondence, or reasonable correspondence here, and quite strong here, between the points under the different approximations. But the weights don't match up. And in fact, there's an extra block under MQL. Well, that seems a bit strange at first, but we can kind of heuristically understand why that's the case if we think about MQL in a bit more detail. Essentially, MQL doesn't properly correct for the attenuation in the parameters in this model. So in some sense, the same values of the parameters are bigger under MQL. So this is why we get this extra block with interior points. We can assess things in terms of the efficiency distribution, or really this is an efficiency function. So we've got the local efficiency as a function of beta 2 under the ML design, which is this top one. as well as MQL and PQL. We've also included a sort of sensible allocation of the 2 to the 2 factorial design to 2 points, 2 blocks of size 2 rather, as a sort of reference design. So in this example you can see that the choice of the factorial would be a bit disastrous. Up here where beta 2 is 10, I think the efficiency is around about, well, I think it's under possibly 5%. The maximum likelihood design looks reasonably robust to the value of beta 2. This kind of middle area of the parameter space is quite a large proportion of it, so we should be more worried about these bits than these bits. MQL looks reasonably close as an approximation in terms of efficiencies, and PQL's, well, worse than MQL, aside from right up here. So it turns out, if you look again in more detail, PQL seems to produce worse treatments than MQL. So in addition to the problem that we talked about earlier with allocation, it gives you worse treatments. So I think this is kind of saying that MQL is a better choice of design criteria than PQL. So to summarize then, we've developed some methods that allow us to take into account the potential effect of blocks when we're designing our experiment. The Bayesian objective function that we've got at the moment takes into account uncertainty about beta and sigma squared, but you could equally well extend that to take into account uncertainty about, for example, the form of the link function, which you might worry about being probit or complementarily log-log. There might also be some uncertainty about the form of the predictor, so which terms to include. These methods, MQL and PQL, also apply to some sort of more general random effects structure. So for instance, you might want to allow the effect of x1 to vary from block to block, or you don't need to change anything about MQL or PQL. You might also want to allow for some correlation between the different random effects. That's fine. Where else can we take this? Well, we could go off and look at some different classes of models that essentially try and capture the same thing. So for instance, HGLMs, which basically generalize the distribution of the random effects, among other things. And another reason that it might be nice to look at HGLMs is there's kind of an inbuilt notion of how well you're estimating your individual level parameters. Wow, I seem to have gone through that incredibly quickly, but overall, overall, yeah, that's everything. So there's some references here for you to follow up on should you so desire, and thank you very much for listening.
So we have plenty of time for questions. I think the wine is not ready yet. So. Questions, please, or comments?
I have a general comment, not only for you. It's about the name Bayesian design. And I think David said pseudo-Bayesian design or robust design, because I think it's confusing otherwise, because Bayesian design, for me, it's when you do Bayesian estimation. So can you comment on that? Or example, I think there are Bayesians in this room. So I think it's confusing to use Bayesian design to do maximum likelihood estimation. I think we should call them robust design or pseudo-Bayesian, or I don't know. It's,
yeah,
I don't know what's your answer or other answers about that. Because if you were to do Bayesian estimation of this, the same thing, Bayesian methods for this GLMMM, how would you call the design? You would call it Bayesian design also. So we have two names for the same thing. So.
Yeah, sure. I certainly think there's a collision of naming there, if not concept. Yeah, we should probably call these pseudo-Bayesian design rather than anything else.
Can I offer a solution called Tim's design, Bayesian design, and what you're referring to the Bayes rule?
Bayes what?
Bayes rule, like the optimal decision on the Bayesian decision theoretic setup. Like when you have a probability, when you have to estimate the inference and the utility function, you try to find the optimal one. It's simply traditional to call it Bayesian design, I think.
I think it's changing. That's why I'm asking that. Whether it used to be called Bayesian design, but nowadays I think I've seen robust design more than Bayesian design. So I just wanted to know whether
there are various ways of achieving robustness.
Pardon?
There are various ways of getting robustness, so that's not unique either.
Yes, I agree.
But in fact, at the last model, there was, I think, that kind of discussion already.
Yes. Okay. So.
I think.
So did you make any decision about that?
Pseudo.
I think that's partly because we all,
There was
are the key leaders in optimal design, so perhaps if you reach an agreement, it could be easier than just going for this debate for years. Or
I recall that Dave in his talk used the term pseudo-Bayesian
Yes.
for when you use Bayesian criterion for the design, not
Yes.
for the analysis. So maybe it can. Will it resolve the terminological issue?
We can set a competition for the best name for this kind of experiments.
I'm a little bit uncomfortable with your efficiency comparisons. So
Right.
basically, all your methods are 0.9999.99. Can you comment? Maybe you choose not the variance not as large as possible, so you can't see the differences. So basically, you end up with a marginal model. It's not convincing.
I'm not sure I quite understand the
Yeah, remember this
question.
relative
So,
efficiency.
yeah, we have this table which has all
right. So
very
you have-
numbers
you have-
very close to 1.
Yeah,
That's just comparing
they're
the different
basically the
methods to
same.
each other.
They're basically
Yeah.
the same. And
Yeah.
to convince us, you have to have different efficiencies.
I thought what he just said was he was comparing methods.
Yeah, so basically, for
Approximation.
small sigma squared,
Very similar.
the different approximations give the same thing. For big sigma squared, we get this
So I
example
simply-
we had at the end, and they all disagree.
I would simply increase sigma squared and would see the differences much more clearly. This is my point.
Yeah.
So that was kind of in the last example. So there we had bigger sigma squareds and there were bigger differences.
So I was going to rephrase that last question more or less in the light of you have the 3 different methods for doing the approximation. Given what you've seen overall, how would you evaluate the trade-offs? And which would you use and when?
Oh, okay. Well, I've never used PQL or MQL2, in short. MQL seems to work better than those in most of the situations that I've seen. I think I've seen another approximation that you could use, which is kind of based on adjusting MQL that would work if you've got a random intercept model with more points per block. But basically, if you're stuck with a large block size, you're not going to be able to do any kind of maximum likelihood. So pretty much your only choices left are MQL.
And there don't seem to be any substantial computational efficiency differences. But they all seem to have basically the same computational complexity. Is that correct?
So, I mean, in general, ML is horrible. At the level of 2 points per block, they're all pretty similar in terms of computational complexity, but there's not really a trade-off because ML does a lot better when you've got 2 points per block. And also, you might be worried that that's not a particularly realistic estimation situation anyway. But for the point of view of comparing the methods, that's what you want to look at. So.
Ask all the comparisons with the factorial design.
Yep.
I think the points were at plus and minus ones. Yeah. Is that right?
I think so, yeah.
So could you, if you just shrunk it in, so if for each factor you just put the points that
Yeah.
and the values which would be optimal if you didn't consider the other factor, and then did a 2 by 2 factorial, it might look much better.
Right. Yeah, okay, I mean, it's certainly something we could try.
Okay.
Sometimes in designs for GLMs, I think it's helpful to look at the induced design space.
Yeah, it's kind of Elfring theorem.
Yeah, well, you divide by the square root of the iterative weights. I just want, it only works for simple first order models, and so I just wondered whether it would provide any insight here or not. I don't expect you to have an answer to that. Let's provide it, you know, it's just a suggestion.
Yeah. I mean, you can certainly get some kinds of analytical results out when you've got a small number of factors or something, particularly for the sort of approximations. Say MQL, you can find out what the optimal design is for a 1-factor problem, or 1 point per block. Horrible like that.
Rounded has a film for GLM of an induced design region, showing how it folds in and out as the parameters vary.
Right.
And you can see, you know, the design points are always at the extremes of this funny folded space. I think it sometimes explains a little bit why these things are moving around and why the weights are changing. Presumably you're exploring trying to explore fairly complicated spaces, or you will be, to get to bigger examples.
Yeah.
Along the same lines, that if the inputs had been continuous, then there might have been mileage in considering a transformation of the design variables, one being your linear predictor, and then you need to choose others, and you can produce, well, again, a standardized design variable, and sometimes you can come up with solutions for that standardized design variable, which then can be transformed back for any parameter value.
So something along the lines of kind of Ken Russell's Poisson stuff, or something like that, you mean? You mean something along the lines of your Poisson paper?
Yeah.
The kind of canonical transform issue?
But once you move into several variables, it's a bit more complicated.
Yeah.
Okay. Any other comments or questions?
Here.
Oh, sorry.
Just a little question about your.
Sorry, could you speak up?
I'm just thinking what I wanted to ask. Concerning the weighted criterion, I prefer weighted criterion instead of Bayesian, just to answer your question. You considered different alpha. Alpha equal to 0 for the logarithm of the determinant, and alpha greater than 0. Is there any reason why you did not consider negative alpha?
Oh, negative alpha, okay.
Which would be more weight in the covariance matrix than in the information matrix.
I think it's just for the reason that in Firth and Hind's paper they kind of look at alpha in the range 0 to 1 over p. Do they not? Is that right? I thought this was to do with concavity of the objective function rather than anything else.
Negative alpha were perfect, as I remember. I'm sure.
Okay. Okay.
Anything else? If not, let's thank them again.